In this video, we're going to come up with a visualization of all 6 trig functions on the unit circle. Our 6 basic trig functions are cosine, sine, tangent, cotangent, secant, and cosecant. We'll be using the angle theta in each case here. So cosine of theta, sine of theta, tangent of theta, and so on and so forth. Now, each of the other 4 trig functions, apart from cosine and sine, can be written in terms of sine and cosine. For instance, tangent is equal to sine of theta divided by cosine of theta. Cotangent is cosine of theta divided by sine of theta. Secant is 1 over cosine of theta. Cosecant of theta is 1 over sine of theta. Those last 4 trig functions exist as long as denominators are non-zero. So the basic building blocks are understanding where cosine and sine are on the unit circle, and then we will build out what that means for tangent, cotangent, secant, and cosecant. On the unit circle, that is the circle of radius 1 centered at the origin. If I have an angle theta that I measure from the x-axis to some line through the origin, well, then the point of intersection with the circle and the terminal ray of the angle is going to be cosine of theta, comma, sine of theta. We can define cosine and sine like that. You can also come up with this using right triangle definitions. So on the unit circle, the measurement from the origin along the x-axis until we get to the x value of that point, that length is going to be cosine of theta. And the vertical length from that point up to the point on the unit circle is going to be sine of theta. So we have this right triangle where one leg is cosine of theta and the other leg is sine of theta. Now, since it's the unit circle, the radius is 1, and we can see this blue line segment therefore has length of 1. Based on that, we get what we call the Pythagorean identity, where cosine squared plus sine squared is equal to 1. That's the Pythagorean theorem with this right triangle here. Now, I want to mention something that we're going to use often. Namely, I want to mention the idea of the complementary angle. We're going to label theta prime in this video as the complementary angle of theta. Complementary means that they add up to 90 degrees, or if we were in radians, they would add up to pi over 2. Now, there's a lot of different places where that complementary angle is going to come up. One place is here at the origin. Notice that the x-axis and y-axis form 90-degree angles where they intersect. Therefore, if theta is the angle that we talked about going from the x-axis out towards the point cosine theta sine theta, then my complementary angle theta prime would be the measure between the y-axis and that ray. Another place we would see the complementary angle is at the other angle of this right triangle with legs of cosine theta, sine theta. So the complementary angle would be on the other side. That's because the 3 angles of any triangle have to add up to 180. Since we have a right triangle, this angle in here is going to be 90 degrees. So the other 2 angles also have to add to 90 degrees. The key to visualizing the other four trig functions is to create a line segment that goes from the x-axis to the y-axis through this point cosine theta, sine theta, that is perpendicular to the line segment from my origin to point cosine theta, sine theta. Perpendicular means that we intersect at 90-degree angles. So we're getting 90-degree angles here and here. Now, what that's going to do, because we're intersecting at 90-degree angles, is that's going to create a couple other right triangles, namely the one from the origin to cosine theta, sine theta, all the way out to this point on the x-axis and back, and also from the origin to cosine theta, sine theta, all the way out to the y-axis and back. And now we have three right triangles. One is the right triangle we saw earlier, whose legs are cosine theta, sine theta. The other goes from the origin to the point on the unit circle and to the x-axis and back. And the last one goes from the origin to the point on the unit circle to the y-axis and back. Now, if you look at the angles that these have to have, the cosine theta, sine theta triangle has to have one angle of theta, the other angle is complement of theta, and then the 90 degrees. Since we have right triangles, if you look at this angle in here on this middle triangle, the one I picture in the middle, this angle has to be theta, and therefore the other angle has to be the complementary angle of theta. In a similar way, since we already know the complementary angle is here between the ray and the y-axis, and we know that we have a 90-degree angle out here, then the complement of the complementary angle is going to have to be theta. So each of these three triangles have angles which are, one is 90 degrees, one is theta, one is the complement of theta. And so the three triangles are all similar. And we know that in similar triangles, the ratio of the sides have to be the same. Remember that in this first triangle, the sides are cosine theta, sine theta. So if we take the similarity between that triangle and the triangle from the origin out to cosine theta, sine theta, and then on the x-axis, what we could do is we could say that the hypotenuse over cosine, notice that cosine is adjacent to the angle theta, is the same as the hypotenuse of this triangle, which I've labeled C, divided by the side adjacent to theta, which is 1. So 1 over cosine of theta is C over 1, and C over 1 is just C. So C is 1 over cosine, which is secant. So that means this length from the origin along the x-axis to the point of intersection with that perpendicular line and the x-axis, that length there, the C length, is secant of theta. If we think of B divided by 1 on this triangle, those are the two legs of the triangle. B is going to be adjacent to the complement of theta. 1 is going to be adjacent to theta. So b over 1 is equal to sine over cosine, or sine over cosine is b over 1. Rewriting that, b over 1 is just b. So b is sine over cosine, which is tangent of theta. With the other triangle, we can do a very similar thing. Once again, I'll label the other triangle with length along the y-axis this time as c, and length from the cosine theta sine theta point up to the point on the y-axis. I'll label that as b. So 1 over sine is equal to c over 1, and then that means c is 1 over sine of theta. B over 1 is equal to cosine over sine of theta, or cosine of theta over sine of theta is equal to b over 1. And that means b is equal to cotangent of theta. So when we put all of those things together on the unit circle, we get this picture. Unit circle says this radius is length 1. The length from the origin along this green line, that length is going to be cosine. The length vertical on that triangle is going to be sine. The length from the origin to this point on the x-axis is secant. The length from the origin to this point on the y-axis is cosecant. Tangent is going to be the length from the point on the unit circle to the x-axis along this perpendicular line. And then cotangent is going to be the length from that point up to the y-axis. So that's what all 6 trig functions look like on the unit circle as lengths. I've set up this visualization in Desmos where we can see that by changing the angle, it changes all of those lengths. So as we change the angle, cosine and sine can change, and that in turn changes all of these lengths, keeping this line perpendicular. So that's what's going on. You can see that as cosine gets really small, secant starts getting larger and larger and larger, and tangent also is getting larger and larger and larger when cosine is getting smaller. Similarly, when sine gets smaller, so the angle gets smaller, sine gets smaller, cosecant and cotangent are getting a lot larger. And in reverse, the tangent and the secant are getting smaller. Secant can go down at smallest, create 1, but that's what happens. At the point where the angle is 0, obviously the cosecant goes away. Because it gets to infinite length, and same with cotangent. And when the angle gets to be like 90 degrees, then secant goes away, it gets infinite, and then tangent would get infinite. So you can see how that moves how each of those functions change as we change the angle. So that's how we can visualize all 6 trig functions on the unit circle with this diagram. And again, the key was creating this line segment from the y-axis to the x-axis that is perpendicular to the ray from the origin to point cosine theta sine theta on the unit circle through that point cosine theta sine theta on the unit circle. You may have noticed that all of our trig functions are paired. We have a sine and then also a cosine, a secant and then also a cosecant, a tangent and a cotangent. Well, the language actually comes from the complementary angle. So the co prefix is actually referring to complementary angle. So in other words, the side opposite angle theta is length sine. The side opposite the complementary angle is cosine. So it is the sine of the complementary angle. That's where it gets its name from. So cosine is literally just the sine of the complementary angle. The same can be said for tangent and cotangent. The tangent of the complementary angle, if you drew this diagram this way, the tangent of the complementary angle is the cotangent of the original angle. And similarly, cosecant is the secant of the complementary angle. Again, just exchange the roles of x and y, and you get that. Another note that I want to state is about the language of tangent. If you know a little bit about calculus, this line that is perpendicular to the unit circle is actually a tangent line to the unit circle at point cosine theta comma sine theta. And so the naming of the tangent function in trigonometry comes from the fact that we're utilizing a tangent line to the unit circle. So those are just a couple of interesting little notes that you can see once you've drawn this picture with all 6 trig functions in relation to the unit circle. That is it for this video. There'll be more videos linked about trig functions in the description of this video.